3D morphable face models have attracted much attention in the past 2 decades. However, previous works assume faces are Lambertian surfaces, limiting the rendering quality significantly. More recently, some works propose to build 3D morphable model for diffuse and specular albedo. However, they require expensive light stage scans for training. In addition, only the specular albedo model cannot represent spatially varying facial specular sureness. In this paper, we propose Reflectance MM. The first 3D morphable face reflectance model with spatially varying BRDF and a technique to train the model with low-cost publicly available data. Here we show random samples drawn from our model. See the plausible facial specularities. Let's dive into the details of our work. Recall that our goal is to learn a 3D morphable face reflectance model with spatially varying BRDF from low-cost publicly available data. To this end, we design Reflectance MM, a novel 3D morphable face reflectance model representation to model spatially varying BRDF of human face. To train our model, we propose a novel technique to learn the model parameters from low-cost publicly available data. To model spatially varying specular sureness and intensity, we represent face reflectance as a Lambertian BRDF combined with the linear combination of several Blindfong BRDFs with different predefined specular exponents. Thus, the reflectance parameters of each face vertex include an RGB color for the Lambertian BRDF and a set of weights for the Blindfong BRDFs. We exploit 2 kinds of publicly available data sources to train our model, the multi-PIE dataset and the FFHQ dataset. In multi-PIE, multi-view images captured under controlled lighting conditions are provided. Using these images, solving reflectance parameters is well posed. However, it only contains a limited number of identities, restricting the representation power of the model. In FFHQ, only single-view images captured under unknown lighting conditions are provided. Thus, solving reflectance parameters from which is notoriously not easy. However, it contains diverse identities, which enable us to learn a powerful model from it. To combine the best of 2 data sources, we propose to train an initial model on the multi-PIE dataset, and then fine-tune it on the FFHQ dataset to improve its generalization ability and expressive power. Using the provided multi-view OLAT images in the multi-PIE dataset, we devise an inverse rendering algorithm to solve the reflectance parameters in the UV space. We then repeat this step to solve the reflectance parameters of all the selected 128 identities in the multi-PIE dataset. Next, we train a PCA model using the solved reflectance maps as our initial morphable face reflectance model. Considering that the multi-PIE dataset only contains 128 identities, which is far from sufficient to capture the variability of human faces, we propose to fine-tune the initial model on a large scale in the wild dataset, FFHQ, to improve its generalization capability and expressive power. However, the FFHQ dataset only provides single-view images with unknown lighting information, thus it is not easy to reconstruct accurate reflectance from them. Our key observation is that, on the one hand, we already have an initial parametric reflectance model that can better formulate the reflectance reconstruction from in-the-wild images. On the other hand, the reconstructed reflectance from in-the-wild data could provide feedback to enhance the face prior knowledge in our morphable reflectance model. Based on this observation, we jointly reconstruct the face reflectance coefficients and update the parameters of our morphable face reflectance model, including the mean and bases. Given a single input face image, we apply an encoder to estimate its lighting and reflectance coefficients. Combined with the precompute geometry parameters, we can obtain the reconstructed face image via a differentiable renderer, and then compute self-supervised loss and jointly update the encoder and our reflectance model. After model fine-tuning, we obtain our final morphable face reflectance model. Compared to the initial one learned from only the multi-PIE dataset with limited number of identities, our final model achieves better face reconstruction quality, especially around the mouth and eyes. We compare our method to BFM and albedo-MM. BFM is a diffuse-only model, while albedo-MM is a morphable model for diffuse and specular albedo learned from light stage scans. We adopt exactly the same CNN-based face reconstruction pipeline to ensure fair comparison. Given a single input image, we first reconstruct its reflectance parameters. We then relight the input image at a novel lighting condition for comparison. Compared to BFM09, our method successfully render plausible facial specularities since we adopt a non-Lambertian reflectance representation. Compared to albedo-MM, our method achieves more realistic results since we can model both spatially varying specular intensity and sureness. Please ignore the color difference and only focus on the distribution of facial specularities since we do not have the ground truth light color information of the multi-PIE dataset. We show OLAT rendering results on in-the-wild images. Given a single image as input, we reconstruct its reflectance parameters using our model and then change its lighting conditions. We show relighting results on in-the-wild images under environment lighting. Our method obtains plausible face relighting results with decent facial specularities. In conclusion, our contributions are listed as follows. We propose the first 3D morphable face reflectance model with spatially varying BRDF and a technique to train the model with low-cost publicly available data. We apply linear sureness weighting into parametric face modeling to represent spatially varying specular sureness and intensity. We propose an update-by-reconstruction strategy to fine-tune our face reflectance model on an in-the-wild dataset, improving its generalization capability and expressive power. Thanks for your attention.